Hello everyone and welcome to lecture. In this lecture we'll be talking about the complex exponential, Euler's equation, and how to represent complex numbers in terms of angles in the complex plane. After this we'll see how to derive various trigonometric identities using this relationship. So far we've seen that we can talk about complex numbers as being numbers in the 2D plane with a real component and an imaginary component. So for any complex number, we can write that complex number as its real part plus I, where I is the square root of -1, times its imaginary part. And we've also seen that we can define things like the modulus of the complex number, where the modulus of the complex number is z times the complex number times its complex conjugate, the square root of that, which is the same thing as the square root of the real part of the complex number squared plus the imaginary part of the complex number squared. So it's really just the radius out from the origin to that point z. So what this means is that we can use our trigonometric identities and our trigonometric functions to re-express the real part and the imaginary part as the radius times the angle, or times cosine of the angle out in the plane of that number. So any complex number can be written in this form, which is sometimes called the polar form of the complex number. Now it turns out that we can even go one step further, and there's a fairly amazing both equation and identity that we can get for any complex number called Euler's equation. Now you can put this on a slightly more rigorous justification using what are called Taylor series, and this is a topic for Calculus 2. So I'm not going to justify this equation in this lecture, but I am going to write it down, and we're going to use it to get a couple simplified trigonometric identities that will definitively hold for any angles. So Euler's equation is the following. It says that for any angle theta, e to the I theta is equal to cosine of theta plus I times sine of theta. And if you stop and think about this, this is a fairly remarkable mathematical identity, because it's relating things like real numbers, so the exponential function, imaginary numbers, so the I it's showing up in this equation, and the trigonometric functions. proving this rigorously requires more mathematics than we have at our disposal in this lecture and in pre-calculus. But it's definitely a very, very useful identity to know and be able to use, because it can help you very, very often derive certain relationships and certain trig identities that you wouldn't necessarily think hold, or that proving in a different manner might be a little bit difficult to do. So it's worth saying here as well that if you believe me that Euler's equation holds, you can get a rather remarkable identity called Euler's identity, by plugging in pi to this expression. Because e to the I pi, assuming this equation holds, is the same thing as cosine of pi plus I times sine of pi. We know that cosine of pi is -1 and sine of pi is 0. So this leads us to the identity that e to the I pi plus 1 is equal to 0. And this is what's called Euler's identity. And it's a truly remarkable mathematical equation. It's sometimes been called the most beautiful equation in mathematics because of the interrelationship here between the exponential, so the logarithmic function, the real numbers, so the irrational numbers, pi, the imaginary number I, and then the integers 0 and 1 here. But let's see if we can use this to prove and show that certain trig identities hold. And this is something that we'll do a couple different times before the course is done. We'll rely on Euler's equation to show us that certain trig functions hold, or trig identities hold. So suppose we want to show, say, what the cosine or the sine of the sum of two angles is going to be. So we can use Euler's identity to get us a very, very nice and quick proof of how to, say, relate cosine of u plus v or sine of u minus v to the cosine and the sine of the original angles. So we'll start with cosine of u plus v here and see if we can show this. And specifically, this is going to rely on Euler's equation and on the fact that we've shown before that the complex numbers are a field. They form a field, so we can do things like take the exponent and do all the sorts of algebraic manipulations that are normal in a field of numbers. So let's consider e to the I of u plus v. From Euler's equation, this is the same thing as cosine of u plus v plus I times sine of u plus v. But algebraically speaking, e to the I of u plus v is the same thing as e to the iu multiplied by e to the iv. Because all of our manipulations for exponents work the same in the complex plane as they do in the real plane, or along the real line for real numbers, really for any field. E to the iu again from Euler's equation, is cosine of u plus I times sine of u. So that's this term right here. And then we have to multiply this by e to the iv, which is cosine of v plus I times sine of v. So we have the multiplication of two sums, which we know directly how to do in the complex for complex numbers. We just do this by again using foiling this multiplication out. So you have to do this times this, this times this, this times this, and this times this. So when we do that, we get cosine of u times cosine of v. Then it'll be minus sine of u times sine of v. And it'll be plus I times cosine of u sine of v plus I times sine of u cosine of v. Let me make a little bit more space here so we can see this. So this is equal to cosine of u times cosine of v minus sine of u times sine of v plus I times cosine of u sine of v plus sine of u times cosine of v. And we see here that we actually just derived two new trigonometric identities. Because in order for these two things to be equal, which they have to be from our algebra of complex numbers, so both these two things have to be equal to one another. We've shown that cosine of u plus v is the same thing as cosine of u cosine of v minus sine of u times sine of v. And we've also shown that sine of u plus v has to be equal to cosine of u times sine of v plus sine of u times cosine of v. So Euler's equation is very, very powerful. It gives us a direct method of calculating and computing relationships like this. So I suggest that you go through and you do this for a couple other combinations, like sine of u minus v, and see if you can get similar trig identities, and go through and kind of test this out. It's really a very, very fast way of deriving relationships between trig functions and additive angles. This is what's called, these two equations are called the sum identities. You can get similar identities for the difference identities, the basic difference identities for trig functions. But these are two of the most basic identities. You can also use these identities if you want to get simpler identities, such as like the double angle identity. That's another basic trig identity that is very, very useful. So once you have, say, like either of these two trig identities, you can go through and look at what happens when you simplify. Say, let's say u is equal to v. Is equal to some theta, some angle theta. Well, then you have cosine of theta plus theta is the same thing as cosine of 2 theta. And then from this identity, because u is equal to v is equal to theta, this is the same thing as cosine of theta multiplied by itself, or cosine squared of theta, minus sine squared of theta. So this is one of the double angle identities. Unless you can consider the same thing with sine of theta theta plus theta. This is the same thing as sine of 2 theta, which is the same thing as cosine of theta times sine of theta plus sine of theta times cosine of theta, which means that sine of 2 theta is equal to 2 times cosine of theta times sine of theta. And these are sometimes called the double angle identities. For any given angle theta, they relate cosine and sine of 2 theta to other combinations of just cosine of theta and sine of theta. You can even simplify some of these even more if you want to. With let's say that take the first double angle identity here. I'll take this double angle identity, and you can write, say, that cosine squared here is the same thing as cosine of 2 theta minus sine squared. And let's actually, just before we solve for cosine squared, let's simplify this a little bit more. So we take the first form, that cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. And you'll recall that from our most fundamental trig identity, sine squared of theta plus cosine squared of theta is equal to 1, saying that the radius of the unit circle is equal to 1. So from that, sine squared of theta is the same thing as 1 minus cosine squared of theta. So cosine of 2 theta is the same thing as 2 times cosine squared of theta minus 1. Or if you solve for cosine squared, cosine squared of theta is the same thing as 1 plus cosine of 2 theta over 2. And this is the first of what's called the angle, or the power reducing identities. Extremely important in calculus 2 when you're doing what's called trigonometric substitution, and you want to know how to take what's called the definite integral of cosine squared. This identity breaks down cosine squared into something that's much more manageable to taking the antiderivative of. We can get one for sine as well if you use the same procedure here, and we showed that the double angle identity for cosine is that cosine of 2 theta is equal to cosine squared minus sine squared, and cosine squared is the same thing as 1 minus sine squared. Then this gives us that cosine of 2 theta is equal to 1 minus 2 times sine squared of theta. And if you solve for sine squared of theta here, you get that sine squared of theta is the same thing as 1 minus cosine of 2 theta over 2. So this is the other power reduction identity. It gives you sine squared in terms of a lower power of cosine. So this has shown how powerful Euler's equation is. Really, Euler's equation allows you to derive many very, very important trigonometric identities that you can then use to simplify trigonometric expressions and solve trigonometric equations. There's also a number of identities for the tangent function as well. So I'm not going to go over those in this lecture, but the idea here is just to show the power of Euler's equation and the complex exponential form of complex numbers. But that will conclude the lecture for today. Let me know if you have any questions, and I hope you learned something.